Hello. Let me get pinned over here. Close the door. Welcome to class. Let me get a few things up and running here. There's the chat and attendance form. Where'd you go? Attendance form. There it is. Here's the attendance form. Do the thing. You guys are posting some good discussion questions on Canvas. I've been trying to help with those, but not help too much, although I might have helped a little too much, so it's okay. But yeah, I like to see that you're interacting with each other. It seems really good. Also, there was something else I feel like I wanted to say. Oh yeah, I posted a couple videos today. One doing a similar-ish kind of linearization of a vector valued function. So kind of like that homework problem that is going on in the discussion with the linearization of sine of x plus y, cosine of whatever that one is. And then I also posted a video about a squeeze theorem question that someone asked me to do. So those are and I did it on the document camera. Let me know, like either if the quality doesn't look good or if it's hard to read, let me know about that somehow. I guess via email or in the discussion, since I've disabled the comments on YouTube, so you can't just comment right there. But yeah. All right. What should we talk about today?
Can we go over min and max?
Definitely. Also, Julie, I like your, I think those, are those artichokes? I can't tell what your picture is of. I'm going to pin it for a second just so I can see it. Oh, I don't know if I can. Oh, well. It looks neat, whatever it is. Sorry. I know it's my face real close. I just wanted to see. Sophia, I like your picture too. I like all your guys' pictures, but that one just looked really interesting to me over there. So, all right. Min and max. So. Yeah, I've got some examples here. 1 second.
Can we also go over a little bit about implicit differentiation?
Oh, sure, yeah. So I'm talking about possibly. Excuse me. Sure, for sure. Yeah, I don't know if I have any of those good to go, but I can definitely, those are not hard to come up with. So, actually, let me try doing, so someone requested that I try doing something other than the whiteboard. Not that I won't use the whiteboard at all, because I like using the whiteboard. But let me try using the document camera today just to see how you guys feel about that. And then we will, maybe I'll try and evenly split between it if you guys decide the document camera is a win. So let me switch my camera here. Oh, except it's not, oh, there we go. Sorry. Turn on. Now it's giving it to me. Okay. So there's the document camera, just like good old times when we were in class and I would use the document camera, except for, you know, it never worked when we were in 17B in Olson. So this is better because this one actually works. All right, so let's look at this problem. We want to find and classify. So I should write the words. Find and classify the relative extrema, meaning maxes, mins, and saddle points for the following surfaces. I know the downside of this is you guys don't get to see my lovely face, but you'll live. Let me look at the lighting as well. Well, that's way too bright. Okay, that's crazy. We don't want that. And let me mirror my video because this looks weird to me. Always with the mirroring, the unmirroring. Sorry. Unmirror video, great, okay. That looks normal. Okay, so hopefully you guys can read that all right. Well, let me know if you can't, if it's, oh, there's succulents, cool, I like the succulents. So here's our surface. F of x, y equal to x squared plus 6xy plus 10y squared minus 4y plus 4. All right, and so to be able to find where you might have a max or a min or a saddle point, just like in 17A, we first have to find any critical values. Now it's going to be a little more complicated because here instead of just setting the derivative equal to 0 and finding the points, we're going to actually have to set each partial derivative equal to 0 and find the pairs of points that satisfy both equations simultaneously. So let's take a look. So, sorry, I got all this paper in the way here. Apologies. Too much stuff. Okay. So, taking the first partial with respect to x, I'm going to get 2x plus 6y plus 0 minus 0 plus 0. I'm going to set that equal to 0. And I'm going to leave it there for a minute. Taking my first partial with respect to y, I get 0 plus 6y minus 20y minus 4. And I set that equal to 0. And then I'm going to find all the solutions to this. So let me point out, 0, 0 is not a critical value. Because although 0, 0 is a solution to this equation, it's not a solution to this equation. So it has to be a solution to both equations at the same time. So what we usually do is we solve one equation for one variable and then plug it into the other equation. And to me, it seems real easy to say 2x equals negative 6y, and then x equals negative 3y. And I'm going to take that, and I'm going to plug that. Oop, that's not what I meant to do. So I feel like I've made a small error, and I did. Do you guys see my error? I'll tell you, it's in the partial derivative with respect to y.
Is it the 6y? Is
Yeah,
it
that
the
should have been
6y?
6x.
Okay, that's what I
Sorry
was
about that.
feeling about.
And so the way I saw that was I didn't have anywhere to plug in x. I was like, oh, that seems weird. I feel like I should. Not that you always do. Right? We could have totally had 6y here, but no, this should be 6x. Look at y magically transform into x. 6x, that's terrible. I'm sorry. This is 6x minus 20y minus 4 equals 0. And then I'm going to plug in x equal to negative 3y. So we get 6 times negative 3y minus 20y minus 4 equals 0. And now I'm going to solve for y. So negative 18y minus 20 is negative 38y equal to positive 4. So y is going to equal 4 over negative 38, which is negative 2 over 19. Beautiful, lovely number. Not really. I'm going to plug that back in up here to get x equal to negative 3 times negative 2 over 19 is positive 6 over 19. So my one critical point is 6 over 19 comma negative 2 over 19. And now we need to classify it. So the way we do that is by finding this thing called D, which is really the determinant of the Hessian. Don't sweat, or it's the determinant of the Jacobian, sorry. So we actually, no, it's the Hessian. Sorry, the Jacobian is the first partial, the Hessian is the second partial. Apologies. So we're going to find the second partials, all of them. Well, all of them, yeah. So looking back up here, just so I have my fx and my fy.
James,
Yes.
for the critical point, what is the x values at? Is it 6 over
19.
19? Thank you.
And y is negative 2 over 19.
Okay.
So finding the second partials, I get fxx, so I'm taking the derivative out with respect to x, which is 2. Fyy, so the partial of y with respect to y is going to be negative 20. And fxy is equal to 6, which, as we expect it to be, is the same as fyx. Now, I wouldn't say this example is unique, but a lot of the times our second partials will actually have x's or y's where we have to plug the point in. This is not going to be the case here. So then we calculate D, which is the determinant of the Hessian. And again, I guess I could show it to you. So it's like this. It's the determinant of this 2 by 2 matrix, which is fxx, fxy, fyx, fyy. But the determinant of that matrix is just fxx times fyy minus, since these are the same, I'm just going to say it's one of them squared. That's usually the quantity that we end up remembering. So in this case, this capital D is going to be fxx, which is 2, times fyy, which is negative 20, minus fxy, which is 6 quantity squared. And then if you were, so here's the thing. Usually you would be evaluating this quantity at the critical point. So we would evaluate this at xy equal to 6/19 comma negative 2/19. The thing about this one is there's nowhere to actually plug that in, so we just get this value. So we end up getting, let's see, negative 40 minus 36, which is negative 76. So here's what this means. If this value D is negative, it means you have a saddle at your critical point. So D being negative means we have a saddle at the critical point. 6/19 comma negative 2/19. And I would love to say that we could look on our cool Desmos graph and try and see if that is actually what we have. I'm going to try and do that real quick because that seems like a cool idea. So give me just 1 second here. Oh, that's not what I wanted. That one's what I wanted. I know you guys can't see my screen yet. I'll share it with you if it actually ends up working out nicely. So here we go, real quick, like x squared plus 6xy plus 10y squared. It's kind of crazy to watch this graph change a whole bunch. I don't know. You can't really. You can sure. I'll share this with you guys for just a second. So I don't really see where the saddle is on this, but if you guys want to look, you certainly can. Yeah, come on. So if you look here, you can. Let me get rid of the +4. Oops! I just deleted it. Can I undo that? Yes, I'm smart. Sometimes
There's the undo button at the.
Yeah. I'm gonna make it -4 just to shift it down a little bit so you can kind of see what's happening here. It's the problem with a lot of these surfaces is it can be really hard to see where the thing is that you're actually trying to see. So there's probably some saddle in some direction here, but I am having a hard time visualizing where it actually is. So I don't know. But there is a saddle point, meaning there's a point where it's a minimum in one direction. It doesn't have to be the X or Y, right? It could be any direction, and there's a maximum in some other direction. So I'm talking to you guys like you can see me. Like I'm like, hey, what's going on? But you guys can't see me right now. I'm sharing my screen. I'm going to stop sharing my screen. And so I'm going to say we have a saddle. I'm going to write one more thing on the document camera. And then I think I'm going to switch over to the whiteboard just because I think I'm more comfortable with the whiteboard. I like being able to see you guys see. Like, I don't know. I like being seen, I guess. So here's what we have. For D evaluated at the critical point, x naught, y naught, which is just fxx times fyy minus fxy squared, evaluated at whatever the critical point is. So let's specify at the critical point, x naught, y naught. 3 possibilities. First possibility is actually the most complicated one. If D is greater than 0, then there is a maximum or a minimum at x naught, y naught. So then there's 2 subcases. It's a minimum if fxx or fyy is greater than 0. Now I want you guys to think about this for a second. If I said fxx was greater than 0, if I said, or rephrasing, if I said the second derivative of a function was greater than 0, that would mean that the function was concave up. And if the function is concave up, We have a minimum at that critical point, right? I'm kind of saying like, oh yeah, my function's concave up. If I have a critical point, it's got to be a minimum. On the other hand, we have a maximum if f(x(x) or f(y(y) is less than 0. For the same sort of reason. If the second derivative is less than 0, it's going to be concave down, and you're going to have a maximum. Something also worth knowing, if d is positive, f(x(x) and f(y(y) have to have the same sign. Right? If these were opposite signs, then you'd have a negative thing minus something positive, which would make the whole thing negative. So it couldn't end up being positive overall if f(x(x) and f(y(y) were opposite signs. So when d is positive, you know that f(x(x) and f(y(y) are the same sign, so you only have to check one of them. The other two things that can happen are, like we saw in the previous example, if d is less than 0, then we have a saddle. And lastly, if d is equal to 0, we don't know. So let me switch over to the board, and I'm going to give you 2 easy examples of those last 2 things, and then we'll get to some more examples. What time is it? Okay, we got all this time. So let me go back to my other screen. I can figure this out. How to use computers. Okay, and that's going to be backwards. I don't know. We'll see. Sorry, I got to figure out which way things are writing here. So let's look at 2 super straightforward examples. One of them you've already seen, or something like it. Let's say we have the function f of xy equal to y squared minus x squared, which we know is a saddle, right? It's the literal prime example of a saddle. And we know that there's a saddle point at 0, 0. Oh, I'm sorry, I missed that question with the negative 20y. So how did I get the negative 20y? Because I had, oh, it was a negative? Oh, shit. Yeah, that's a good, so if you have questions like that and you don't see me hearing them, speak up, because yeah, that's a total mistake. So that is an error. If we go back and look, oh man, so let's go back and look. I hate when I make mistakes. We'll do it real quick then. So it should have actually been fx equal to 2x plus 6y equal to 0, and fy equal to 6x plus 20y minus 4, 0. Here we're still getting x equal to negative 3y. Here if we plug that in, that's much. I was like, why are these numbers so gross? Okay, so then we're going to get negative 18y plus 20y minus 4 equal to 0. We get 2y equal to 4. We get y equal to 2, which is so much better than y equal to whatever. And we get x equals to negative 3 times 2, which is negative 6. Okay, so then let's take a look here. fxx is still 2. fyy is positive 20. Is that what we had last time? No, that's not what we had last time, right? We had negative 20 last time, right? Sorry. Yeah, fyy is positive 20. Maybe that's why the graph wasn't looking like what I thought it should look like, because we actually didn't have a saddle point. So, and fxy is 6 still. So then the determinant of the Hessian here is going to be this times this minus this squared. Yeah, okay, good. That makes me feel a little bit better, because I was worried, like, why does that picture look so wrong? Okay, so this is actually going to be 40 minus 36, which is 4, which is positive. Now, since the determinant of the Hessian is positive, we just call it D, but like, that's what it is. That means we have a maximum or a minimum. And we have to look at one of the second partials, either fxx or fyy, to determine what it is. So we notice that both fxx and fyy are positive. So I should say, right, we have a max or a min. because of this being positive. But since the second derivative with respect to x or with respect to y is also positive, that means we have what? Do we have a max or do we have a min? I know nobody wants to talk. All right, since the second derivative is positive, that means it's opening upward, right? It's concave up, so that means we have a minimum. So we have a min at that point, negative 6,2. Much nicer than, yeah, sorry about that. So there is an example of having a minimum. Also, for anyone who hasn't gotten to it yet, please do sign the usual sign-in sheet only once, please. A couple people, I think, accidentally did it twice last time, so just one time. Only one time. Okay.
So whenever d is greater than 0, it's a minimum, and then whenever it's
I'm gonna stop it right there. Whenever d is greater than 0, it's a maximum or a minimum. And you have to do more inspection. So if you get d being greater than 0, then you look back at fyy or fxx. And you say, oh, these are also positive. That means it's concave up, like a cup, which means we have a minimum.
okay. Thank you.
But if these were both negative, then they'd be concave down and you'd have a max. And you'd still have d being positive. Yeah, very good question. Okay. So let me show you two real simple examples the right way. So f of xy equal to our usual y squared minus x squared saddle. Here, fx is negative 2x, fy is positive 2y. If I set those equal to 0 to find the critical points, I get one critical point. It's 0, 0. X has to be 0 and y has to be 0 to solve both of these simultaneously. Looking at the second partials, fxx is negative 2, fyy is positive 2, and the mixed partial fxy is 0. So then capital D is this times this minus this squared. So it's negative 2 times 2 minus 0 squared. That's going to be negative 4, which is notably negative. And whenever D is negative, we know we have a saddle. So that means, oh yeah, we have a saddle at the critical point 0, 0. Again, we already knew this, but this is how you would show that you have a saddle somewhere. By getting that value for D is negative. So whenever D is negative, you have a saddle. Whenever D is positive, you have to do more work to determine if it's a maximum or a minimum. And then sometimes you have something terrible where D is equal to 0. So here is a very typical example. I'm going to use a little bit more light in here. That's better, yeah. So let's say I have the function d, dumb, sorry, f of xy equal to, let's make it interesting, 81 minus x to the 4th minus y to the 4th. And if I just go about this using the tool we just talked about, I'm actually not going to get what I need. So let's take a look here. Fx is negative 4x cubed. I'm set that equal to 0. Fy is similar to negative 4y cubed. I'm going to often, so again, we'll see some different examples here in a minute, but a lot of the times the critical point, I shouldn't say really critical value, it's the critical point because it's a coordinate, is 0, 0. And then if we find the second partials, fxx is negative 12x squared. Fyy is negative 12y squared. Fxy is 0. So if I find d, it's going to be fxx, which is negative 12x squared, times fyy, which is negative 12y squared, minus 0 squared. Now, I should say this problem is slightly different in that in the previous one, let's go back for a second, I should have actually been saying I'm plugging in d at 0, 0. It's just that there was nowhere to plug in 0 for x and 0 for y, so I kind of ignored it. Here, we actually do have to plug in 0 for x and 0 for y. Look what happens. When I plug in 0 for x and 0 for y, I get exactly 0 times 0 minus 0, which is 0. So what this tells me is nothing. I don't know if I have a max, a min, or a saddle. So these kinds of questions usually require some sort of further inspection, but this one was designed to be knowable fairly easily. So here's the thing. My function, f of x, y, I could totally write it as 81 minus x to the fourth plus y to the fourth. When you see things like x squared plus y squared, or x to the fourth plus y to the fourth, or x to an even power plus y to an even power, you should automatically think, oh, I am seeing something that is always positive. This thing here is always positive. Meaning, if this is always positive, the 81 minus this, well, when x and y are 0, you're going to get 81, right? F of 0, 0 is 81. But then any other values you plug in for x and y, it's going to make this smaller, right? F of x, y is going to be less than 81 for any other coordinates of x and y. But that's exactly what it means to be a maximum, right? This point, 0, 0, 81, if you like, right? Or this, right, this point on the surface, 0, 0, with a z value of 81 is the biggest thing I've got. Nothing else can be bigger. So sometimes you just have to kind of have an idea of how things look. Also, we could graph this one. Actually, here I think the graph on Desmos might actually be worthwhile. Let's take a look here. I might have picked too big a number, but let's take a look. Come on, let me, sorry, one thing real quick. Yes, reload, apologies. Sorry. I moved around my axes and things look kind of crazy. Oh yeah, it's super too big. I'm gonna make it just a little bit smaller. Okay, so I changed my function just a tiny bit, but let me show you. It's easier than drawing it because my drawings don't look great. So here is what that function kind of looks like. I did 9 minus x to the fourth, y to the fourth. It's the same idea, right? The top is up here at 0, 0. I'm pointing at my screen like you guys can see where I'm pointing. The top is up here at 0, 0, comma 9 or 0, 0, comma 81. And then any other x or y values is going to make it get smaller. And if we rotate it around this way, we can kind of see, oh yeah, look, right? The top is definitely in the middle and it's clearly a maximum, right? There's definitely nothing that could be bigger than that. So sometimes finding the determinant of the Hessian is not going to be a sufficient method for determining if you have a max or a min. You won't see a lot of these, but occasionally people like to be like, hey, by the way, there's this other thing we've got. Okay. What time is it? Okay. Let's do one more example, I think, and then I'll talk a little bit about implicit. I don't know if I have any good examples off the top of my head, but I will make some shit up. So let's see. I had a couple other examples here. I really want one that's got something fun. Well, we might do 2 examples. Let's try this one. F of x, y equal to 6x squared plus 6y squared minus 3x squared y minus y cubed. And again, we're trying to find the relative extreme. Oh, you might like to see my screen. Sorry, I'm a fool. There we go. Or my board. 6x squared plus 6y squared minus 3x squared y minus y cubed. And again, we're going to find the partials. So we're going to do partial with respect to x. So the derivative here is 12x. Derivative here is 0. Derivative here is 6x times y. Derivative here is 0. Similar deal here. 0, 12y, negative 3x squared, minus 3y squared. Well, that looks challenging. Okay. So I'm going to take this and I'm going to factor. So factoring is good. I can factor out a 6x. I'm left with a 2 minus y. Well, this is actually pretty great because there's two different solutions. One solution is x equal to 0. The other solution is y equal to 2. Now, don't make the mistake here of thinking 0, 2 is a critical point. 0, 2 is not a critical point. Because if I plug in 0 for x and 2 for y, I'm going to get 24 minus 12 equal to not 0 over here. Right? So these are just two different things. So first, I'm going to plug in x equal to 0 into this fy. And I'm going to solve for the other value, the other variable y. So plugging in x equal to 0, I get 12y minus 0 minus 3y squared equal to 0. Factoring out of 3y, you get 3y times 4 minus y equal to 0. So I get y equal to 0 or y equal to 4. So from x equal to 0, there are two critical points. There's the critical point x is 0 and y is 0. There's the critical point x is 0 and y is 4. And you can check that these are actually critical points by plugging them back into either equation. If you plug in 0, 0, obviously this is going to be 0. If you plug in 0, 0 for this one, obviously this is going to be 0. If you plug in 0, 4, it's a little less obvious, but let's check. If I plug in 0, 4, if I plug in x equal to 0, I get 0 minus 0, done. If I plug in x equal to 0 and y equal to 4 here, well, this part's 0, and if y is 4, 12 times 4 is 48, minus 3 times 4 squared is 48, which is equal to 0. So these are both critical points. And I'm also going to get a critical point by plugging in y equal to 2 into this fy partial. So I'm going to get 12 times 2 minus 3x squared minus 3y squared equal to 0. Sorry, I said y squared. I should have said 12y. So sorry, 2 squared. 12 times 2 minus 3x squared minus 3 times 2 squared equal to 0. I'm going to solve for x. So 24, 3 times 4 is 12 equals positive 3x squared over on the other side. 24 minus 12 is 12. 12 divided by 3 is 4. So x is plus or minus 2. So here I'm also getting the critical points 2, 2, where x is positive 2 and y is 2, and 2, negative 2. So there's actually 4 different critical points for this function. And we're going to test each of them to see if it's a max or a min or a saddle. Okay. So we're going to go to the board. So we'll find the determinant of the Hessian and then we'll write down critical points. So just as a reminder, fx is 12x minus 6xy, and fy was 12y minus 3x squared minus 3y squared. Sorry. Yeah. I feel like there's something I wanted to say here. No, I guess not. Okay. So fxx, partial this with respect to x, is 12 minus 6y. Fyy, partial of this is going to be 12 minus 6y. That's interesting. Kind of a coincidence. And then fxy is going to be, should be negative 6x. And that is the same as fyx, right? Because you partial this with respect to x, yeah, it's negative 6x. Cool. All right, so our capital D is this times this minus this squared. Now, instead of writing this times this, I'm just going to write 12 minus 6y squared. Minus this squared. And then I'm going to plug in my various critical points. I've got 0, 0, and what else? 0, 4. And 2, 2, and 2, negative 2. All right, so let's do it. So D evaluated at 0, 0 is going to be 12 squared minus 0, which is positive, which means we have what?
Max or min?
Exactly, max or a min. What I say is it means we have more work to do. So we have more work to do. So then we go back and we look at fxx and fyy, and we plug in 0, 0. If I plug in 0, 0, fxx evaluated at 0, 0 is 12, which is positive, which means we have a
Maximum? No, wait, minimum. Sorry.
yes, a minimum, right? Because it's concave up. And then we just do the same thing for the other points. So D of 0, 4 is going to be, again, 12 squared minus negative 6 times 4 is negative 24 squared. I don't actually care about the numbers here, right? I can figure out 144 minus whatever that is. I think it's 400, I don't know, 576, I think. But the point is, I know that this is bigger than that. So this minus this is going to be negative, which means I have a saddle. Okay. Looking at the last ones, D evaluated at 2, 2 is going to be, let's see, so if I plug in 2 for x and 2 for y, I'm going to get 12 minus 12, which is 0 squared, minus negative 12 squared. That's going to be negative 144, which is less than 0. So we have a saddle. And it's probably going to be the same for the other one, but let's double check. It might not be. I could be wrong. I am wrong. That's fine. D of 2, negative 2 is, if I plug in 2 for x and negative 2 for y, I get 12 minus negative 12, so I get 24 squared minus negative 6 times negative 7 positive 2 is negative 12 squared. This one is positive, right? Because this is definitely bigger than that. So then I have to check one of the second partials. I'm going to check fxx again, evaluated at the point 2, negative 2. Is going to be, well, if I plug in negative 2 for y, it's 12 plus 12, which is 24, which is positive, which means I have a minimum again. This is a good problem. There's a lot of points to find here. Yeah, I like this one. Yeah. All right. So let's look at something different. Sorry, if you guys still want to see that on there. I don't think anyone's coming, but I'll just put the attendance form up there one more time just to make sure everyone has a shot at it. Please do fill it out. Or you'll get a very nice email from me saying, hey, you didn't fill it out, but you were there. Please go fill it out. Okay, so implicit differentiation. So just like in 17a, when we did implicit differentiation, or maybe 17b, I don't remember if it was 17 or b, where we did implicit differentiation, where we said, oh, y is a function of x, we have all these x's and y's jumbled together. We're going to do the same sort of thing now, where we're going to say z is a function of x and y. We're going to jumble things up together, and we're going to find the derivative of z with respect to x or y, where we're using the, what's the word I'm looking for? We're using the assumption that z is a function of x and y, even though it might not actually look like one. So here's an example. I'm just making this up. It might be terrible. X cubed z squared plus e to the x z y squared equal to 49 minus, this is going to be awful. Let's not make it too awful, James. Okay, hopefully this isn't too bad. So I want to find, I think I'm going to do del z del y first, because that seems like it might be easier. All right, so I'm taking the derivative of everything with respect to y. So here I have to use the product rule. Well, not really, actually, right? Because x cubed, if I'm differentiating with respect to y, is just going to be a constant. So here's what I'm going to say the derivative of this part is. I'm going to get x cubed, the constant, times the derivative of z squared, which is 2 times my stuff, times the derivative of my stuff. All right, for e to the xz times y squared, now I am going to have to use the product rule. Because this part here, e to the xz, is a function of y, because there's a z in it, and z is a function of x and y. And this part here is also a function of y. So the derivative of e to the xz is e to the xz times the derivative of xz. The derivative of xz, well, again, x is a constant, so it's just x times del z del y times y squared. This might actually work out, so not too terribly. Plus, now I'm going to do the other thing. I'm going to leave this alone. And I'm going to multiply by the derivative of y squared, which is just 2y. Equal to, the derivative of 49 is 0. The derivative of x cubed is 0 with respect to y. Okay. So after you do this first step where you differentiate everything, the rest of it is just cleaning up the algebra, which is messy, but not too terrible. So I'm looking for all the things that have my partial.
Is del z dy similar to z prime or y prime, or is that?
You could also call this zy, right? The partial of z with respect to y. Right? So I differentiated with respect to the variable y. That's why I got zeros over here for 49 x cubed. So now I'm just trying to solve for this. So this actually isn't too terrible. I'm going to bring this term over to the other side, and I'm going to factor out the del z del y from each of these. So I have del z del y times x cubed times 2z. I'm going to write that as 2x cubed z. And then I have del z del y factored out times e to the xz times x times y squared. Equal to, I'm going to subtract this over to the side and get 2y e to the xz. And then finally, to solve for this, I'm going to divide by all that. So del z del y equals 2y e to the xz divided by 2x cubed z plus, I would probably write this as xy squared e to the xz.
Wait, James, for the part where it says 2y times e to the xz, shouldn't that be a negative?
It should be negative. Thank you.
Yeah.
Good call. Yeah, I missed that. So it's similar to what we did before with implicit differentiation, where once you differentiate both sides, then you're just grouping all the things that have your derivative and factoring it out and dividing out what's left over. But it obviously looks a little bit grosser. I probably picked the kind of extra gross example. I do feel like it's worth our time to try and do the other direction. I mean, or the other partial, meaning let's do del z, del x. So I'm writing this down on the other side of the board, and we'll try that one. Or I could erase this. No, I'll leave. Yeah, no, let's not erase. Okay. Let's see. So my function was, sorry, x cubed z squared plus e to the x z y squared equal to 49 minus x cubed. And now we're going to differentiate with respect to x, right? So we're trying to find del z, del x. So now, here we are going to have to use the product rule because it's a function of x times a function of x. So it's going to be 3x squared times z squared, right? Differentiate this part, leave that part alone, plus, then you do the opposite. X cubed times the derivative of z squared is 2z times del z del x. If you want, you can write zx here. I prefer to write the del's. Plus, okay, this y squared is just a constant, so it's going to hang out. But the derivative of e to the xz, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But the derivative of x times z, well, since they're both functions of x, I have to use the product rule. So the derivative of x times z is derivative of x times z plus x times the derivative of z, right? This is the derivative of x times z. And it's equal to the derivative of the right-hand side, which is negative 3x squared. Whew, fairly thick. This one has an additional algebraic terrible thing in that to get the del z del x here, you have to distribute this to each of those terms. So let's see what I've got. I've got 3x squared z squared plus 2x cubed z del x plus y squared times e to the x z times z. That's going to be y squared z e to the x z. And then times that is going to be y squared x times e to the x z times del z del x. So that's a lot. So x y squared e to the x z del z del x equal to negative 3x squared. And then these terms here both have my derivative del z del x. I'm going to leave them on the left. The other terms are going to get subtracted over to the right. So I'm going to have, and I like to do the factoring this time as well. So I'm going to factor out the del z del x in these two terms. I'm going to have del z del x times 2x cubed z plus xy squared e to the x z equal to negative 3x squared minus 3x squared z squared minus y squared z e to the x z. And then finally, we solve for this by dividing by that. So our final answer here is going to look super gross. It's going to be all that. That's a z. I know. Divided by all this. Gross. So just remember that when you're doing these, you're still using, right, if you're differentiating with respect to x, you're still treating y like a constant, but you're also treating z like a function of x. So whenever you differentiate something with z in it, you always end up having to multiply by z prime or del z del x, whatever you want to call it. All right. I think that's all I've got for today. I'm going to try and make, I think I have a couple of things I want to, a couple of videos I want to make for you guys. Maybe I'll try and do that today. And what else? I don't know. I guess I'll see you guys on Friday. Let me know if you have any questions. Keep up the discussion. I like the discussions you guys are doing in Canvas. I think it helps out your fellow students, and I'm happy to answer questions as nicely as I can when I have the time. So yeah, keep asking questions or posting things there, and I will be sure to keep up with it. All right, take care. I'll see you guys later.